Problem 1 of kinematics. This involves two objects, a stone that falls vertically downward and a boat that goes horizontally to the right. So a stone falls from a height of 50 meters above the water. So this is the water surface. If it falls directly into a boat moving with constant velocity, v, let's say, which is 10 meters from the point of impact, find the speed of the boat. So the situation is like this. The boat is moving to the right, and exactly at this point, the rock falls. And by the time the boat gets here, the rock falls into the boat. Of course, the rock or the stone falls from rest, and v is a constant. So we have set the position of the stone along the y-axis and the boat along the x-axis. Now we can take this point, the point of impact, to be the origin. So the initial position of the boat can be taken to be x equals to minus 10. And the initial position of the stone can be taken to be y equals to 50. Let's set up the equations. First, for the stone. Now these are kinematic equations because stone is falling down with a constant acceleration equivalent to the acceleration of gravity. So let's start with the position equation. The position of the stone varies in the following manner. So the equation is half. The acceleration of that stone is minus g, because gravity is acting downward, t squared. It falls from rest, so the initial speed for stone is 0. So there is no ut term there. And y naught, or the initial position of the stone, is y equals to 50. So you have to add that 50. So note that at t equals to 0, y is 50, as it should be. Next, equations for boat. Now it's moving along the x-axis, so it's moving with a constant speed. The position of this boat varies quite simply as that. However, there is an initial position of x equals to minus 10, which must be included. There is no acceleration for the boat because it's moving with a constant speed along the x-axis. Before we proceed to determine v, we need to figure out time. What time are we talking about? The stone takes a certain amount of time to travel that distance of 50 meters. And at the same time, the boat would take the same amount of time to cover a distance of 10 meters to the right. So we need to find that common time. Let's call that common time capital T. We can use the stone data to get that. At t equals to capital T, the y-coordinate of that stone is 0 because it will drop at the origin. So setting y equals to 0 in this equation, we get 0 equals minus half g capital T squared plus 50. Note that g is 9.81 meter per second squared. So let's substitute in the value of g into that equation and we can figure out the capital T. And you'll get capital T equals 50 times 2 over gravity square root, which will give you 3.19 seconds. And now we know, using this equation, at t equals to capital T, or 3.19 seconds, the coordinate of that boat is the origin, x equals to 0, because the boat will get to that point. And substituting these numbers inside that equation, you get 0 equals v 3.19 minus 10. And you can solve for v, which will give you 3.13 meter per second. And that solves the problem. Problem 2. Graph below shows the motions of two objects, A and B. So we are dealing with position time graph. The blue graph refers to object A, and the green graph refers to object B. We are told that these two objects, they move towards each other. We are given two coordinates. These are the initial coordinates. So the initial coordinate of object A is 250 meters. So that is this point right there. And the initial position of object B is minus 40 meters. And that is this position right there. A has a constant speed of 20 meters per second, as represented by this straight line. Object B starts from rest. Find the magnitude of the acceleration of object B. So we are dealing with two objects moving along x-axis. So that is the situation that we have here. Let's write down equation for object A, the blue line right there. The kinematic equation describing coordinates of an object moving with constant acceleration is given by the following: half at squared plus initial speed time plus the initial coordinate. Now, applying this equation to this line, we see the following. A has a constant speed along the x-axis, so there is no acceleration, there is no term. The first term, half at squared term, goes to 0. Now, we have speed, and that speed is constant. However, this speed, as described by the negative slope of this graph, must be negative. So the second term would assume minus 20t. Now this x0 here is the initial coordinate. It starts from there, and we know xa0 is 250, so that's positive 250. So there we have it. The change in position for object A is given by minus 20t plus 250. Now let's look at object B. Object B starts from rest, so its initial speed is 0. I'm going to distinguish the two x's with a subscript. Now xb, the acceleration is something that we don't know, so let's leave it as an unknown. Half abt squared is the first term. Starts from rest, so the ut term goes to 0. Object B does not have a ut term, but it has initial position xb0, which is a negative number. It's minus 40, so that minus 40 must be included. And there we have it, the complete descriptions of positions of these two objects with time. Now let's look at the graph. At t equals to 10, the two graphs intersect, so the two paths cross each other. So at t equals to 10 seconds, xa must be the same as xb, and this is the information we need to determine the acceleration a sub b. So substituting this information in here and here, we see that minus 20, time is 10 seconds, plus 250 equals half acceleration, which we don't know, t squared is 10 squared minus 40. So the left-hand side is xa, the right-hand side is xb. So the left-hand side is minus 200 plus 250, so that is 50. The right-hand side is half times 100, so that is 50 ab minus 40. And we can solve for the unknown acceleration. So the acceleration of object B turns out to be 1.8 meter per second squared. Problem 3. A car starts from rest at traffic light with a constant acceleration of 2.5 meters per second squared. At the same time, a truck traveling with a constant speed of 8 meters per second overtakes and passes the car. So we shall represent the traffic light as x equals to 0. The motion is along the x-axis, let's say. The yellow represents the motion of the car, and the green represents the motion of the truck. Of course, keep in mind they move along the same line. Of course, I'm representing one on top of the other to facilitate the writing of the equations. What we are interested in is how far beyond the traffic light will the car overtake the truck, and what is the speed of the car at that instant. Let's write down the equation, kinematics equation for car and truck. So for car, the equation representing the position of the car is given by following. So it starts from rest, so the initial speed is 0. It has acceleration, so half a is 2.5 t squared. There is no ut term. And the initial location is where the traffic light is, so it's x equals to 0. So 0. The truck, as it passes through this point, it's moving at a constant speed. I'm going to denote the position of the car with a subscript c and position of the truck with subscript t. And its position, x position, would change in a following manner. There is no acceleration because constant speed along the x-axis, so the acceleration of the truck is 0. It will have the ut term because it has speed, which can serve as an initial speed, so 8t. And we start timing the motion at x equals to 0, so the initial position can be taken to be 0 as well. Let's assume the car overtakes the truck here. So the same x position for both, so xc equals xt. xc is half 2.5, let's say it happens at t equals to capital T, equals xt. xt is 8 times capital T. The first thing is to figure out the time at which that overtaking occurs. So one of the t's will cancel, giving you capital T as 6.4 seconds. At t equals to 6.4 seconds, the car will overtake the truck. So how far beyond the traffic light will that happen? That is that distance. So it's quite simply xc evaluated at 6.4 seconds. And that is just half 2.5 6.4 squared, which is 51.2 meters. So that's part A. Part B, what is the speed of the car at that instant? The speed is given by the second kinematic equation. So Vc at some time t equals the initial speed of the car. Since it starts from rest, it's 0, plus the acceleration of the car, which is 2.5 times t. So the speed of the car at t equals to 6.4 seconds is therefore 2.5 times 6.4, which is 16 meters per second. And that solves the problem. Thank you for watching.